Hi folks, this is me, I'm Matt Jarvis. I'm a Senior Developer Advocate at Sneak, and Sneak are a cloud-native application security company. So the story of the last decade or so in software development has really seen the boundaries of what's an application, what is operations, what constitutes infrastructure, becoming increasingly blurred. The old view of the world was that the application was the only piece under the responsibility of the development team. And all these other elements of the stack sat under IT operations, with security usually a step right at the end of the deployment process. But the world we live in today is one where infrastructure and workloads are almost completely tied together. Everything's declared as code, everything's a software development practice, and there's really no difference between our workload and the computing infrastructure that goes along with it. And by infrastructure, I don't just mean the underlying compute technology, but also the configuration and the operational policies that control those capabilities. And as a community of practitioners, we've discussed in lots of detail this blurring and eventual consuming of the boundary between development and operations. But in lots of cases, we haven't really considered how that impacts on how we model and how we practice security. In lots of organizations, security is still considered to be somewhat of an external practice that exists only when our applications are deployed and operational. But this is pretty much unworkable in the era of continuous integration, continuous delivery. As we've seen, development-driven teams now have responsibilities for most of that deployment stack. And so this gives those teams a much greater responsibility for ensuring that these things are secure. By the time our code and our infrastructure is deployed to production, it's really far too late to deal with the implications of security issues. And we can't slow down that velocity to introduce security gates in the way that things used to work, because velocity and time to market is clearly the differentiator for businesses to succeed. So that presents us with a set of unique challenges around security. How do we make sure our applications and our infrastructure are secure when our working practices are evolving into these super fast delivery pipelines? Security still matters, and as we've seen repeatedly over the last few years, security breaches can have a really big impact on businesses, both from a financial perspective in terms of bottom line and potential fines, but also on how trusted our customers see us as. And trust's really one of the key metrics for successful businesses in the cloud era. So let's start by taking a look at the different classes of things we probably need to be looking at to ensure that we've got security considered within our workflows. Firstly, the applications that we're creating, our workloads. And modern applications are usually composed of a relatively small core of homegrown code, along with a huge amount of third-party, usually open source modules. And this is great news for application development because the availability of modules and library code means we get to develop applications faster, we have to write less code, and we don't need to reinvent the wheel all the time by solving the same problems over and over again. And anyone who develops in Java, in Python, in Node, in Go is going to recognize this pattern. And in all of these ecosystems, the number of vulnerabilities is growing. And this isn't necessarily because code's getting more insecure. It can be just because there's more code being written, more libraries, more modules being written. Maybe we're getting better at working out what's vulnerable. But in the end, this all means more opportunities for these vulnerabilities to be exploited. And when we import something into our code base, it can have a very large dependency tree, both in terms of direct dependencies that are the dependencies of the thing that we're importing, but also indirect dependencies, so dependencies of dependencies. And so we potentially bring in a huge amount of other code that we might not even be aware of. And typically over 70% of all security vulnerabilities are found in these indirect dependencies. So these are the ones that we have much less control over, and we might not be aware of them at all. So as an example of that, here's an exploit from the Node community. It was introduced into NPM in 2018. And this is supposedly a library to parse HTTP headers, but it's actually a remote code execution exploit. It's about 40 lines of code to process remote JavaScript executed on the server via using specially crafted commands in the HTTP request. And this was hidden behind a tree of other dependencies, and it eventually ended up, the direct dependency ended up being used in Mail Parser, which has a huge amount of downloads every month. So it's pretty easy to see how in large developer communities, these kinds of indirect dependencies can be used to hide exploitable code. So vulnerabilities in those third-party dependencies is super important because they make up such a large part of our code bases these days. But as I said earlier, the lines between our application and the container it runs in are becoming really blurred. The container is the delivery mechanism for the application. They're typically developed at the same time, usually even by the same team. So for all intents and purposes, we can consider them the same thing. The application never exists without that container image. And like the availability of library code, the huge growth in public container registries has been great for the ability to run prepackaged software super easily and for us to consume that in our own infrastructure, but they are also a big source of vulnerabilities. And when we look at the container landscape, although best practices are emerging around things like building minimal containers, there is still a huge amount of people using containers directly from the upstream repositories. And lots of these can have very large numbers of vulnerabilities in them. And we're presented with lots of possibilities for attack vectors. So it's important that our developers working with container images understand the scope for introducing vulnerabilities here. And there's also a long tail taking the path of least resistance by giving applications containers based on full operating systems, for example. And when we look at operating systems in general, the amount of vulnerabilities in base operating systems is really massively growing. And that's partly because operating systems by design ship with a lot of software in them. And, you know, if we look at operating systems like that, you know, we can see that they kind of break the paradigms of containers in the sense that what we want to be doing is producing a absolutely minimal package for our application. But there's still a lot of people using these kind of bigger images for workload deployments. And we can also see that a lot of people don't think about emerging vulnerabilities once their workloads are in production. So an image that when it was first deployed didn't have vulnerabilities in it, there may be new vulnerabilities that have been discovered since the image was built. And if you're not looking at containers you already have in production, then you're never going to find out if they're now vulnerable. And fixing these things isn't usually very hard. Over 40% of Docker image vulnerabilities can usually be fixed by upgrading the base image. And around 20% of them can be fixed just by rebuilding them. A lot of containers will have upgrade steps during in the Docker file, and they'll get run during the build process. And as we've moved wholesale into cloud and now into Kubernetes, configuration is almost entirely in code and it's part of our development workflows. And by configuration, we can include all of our Kubernetes YAML, our Helm charts, our automation, our Terraform, and all of the policies and configuration that goes alongside that. And this is a massively growing field, as we can see from the amounts of this kind of code that are in GitHub now. We're really only just starting to view that as something that we need to consider from a security perspective. Systems like Kubernetes are increasingly complex. And as we've moved the responsibilities for delivering that kind of code into our development teams, there's clearly space for misunderstandings about how things work. This can be compounded with things like service meshes, which increase that complexity even further. And with this much code out there in public repositories, we can again see the potential risks of path of least resistance, where we might be using existing code as templates when we might not fully understand how that thing works. And these are all very important in terms of the security of our environments. This quote from the Open Web Application Security Project is a little bit old now, but it still proves the point that a huge amount of security breaches are coming from misconfigurations in infrastructure. And most really large exploits over recent years have been this combination of application level vulnerability combined with infrastructure misconfiguration, which has then allowed the attacker to widen the blast radius and extend the exploit. And as I'm sure most of us have seen, there's many real world examples of this. Things like cloud credential leakages through source code repositories, or of Kubernetes clusters infested with crypto miners. And when we look at this space in terms of Kubernetes, it's important to understand that Kubernetes really doesn't give you any guardrails. It's insecure by default. And this is on purpose. You know, it's meant to be highly configurable, and users are expected to make these decisions by themselves. You know, by default, there are no resource limits set. That means a pod can consume as much resource as the kubelet will let it. And this has the potential for denial of service attacks, affecting a much bigger scope than just a single application. And Kubernetes will also quite happily let containers run as root. And with a huge amount of containers in public registry still being configured to run as root, this opens up really big security implications. A compromised pod running as root has the potential to escape the container. And so we really need to be limiting the potential for these kind of attacks. And very few applications actually need root access in order to run. Writable file systems inside containers is also a risk point. If that container is then exploited, it allows an attacker to download new software, make changes to configuration, and generally be able to extend the access that they've got already. And containers also have access to the full range of capabilities configured by default in the container runtime. And capabilities, for those who aren't familiar with them, are kernel level permissions. Many of these granular kind of permissions won't be required by your application, and having them turned on just creates additional vectors for attackers to use should that container be compromised. So where do we start with all of this in terms of modern Git-driven workflows? Well, the emerging answer is that we have to shift our security practices far to the left and embed security into our development pipeline. So we share that burden of security responsibility across our development teams. And this is really where this concept of DevSecOps comes into play, that we need to integrate security considerations into our workflows in exactly the same way that we merge development and operations over the last few years. And where do we start in practice? Well, the obvious first place is at the developer. We need developers to have insights immediately into potential security issues, tightly integrated into their workflow, so friction-free, and that means tooling that's available from local command lines, integrations with IDEs. So we need to reduce the overhead for developers to use these kind of tools right at the point they're working, before code even gets anywhere near our repositories. And the tooling we use has to provide developers with the right information to be able to make security decisions, not just lists of CVEs, but tools that give us insights into how severe something is, how exploitable it is, and remediation advice, like how do I fix it? Because that's what really we care about, is how do we go from the state we're in now to a better state. And as we saw earlier, we'll want to be able to look at all of those classes of things that we're interested in. So third-party dependencies in our code, what's going on in our container images, and all of that infrastructure code that we're putting in at this point. And you can do all of this with Snyk for free. So our second touch point is clearly Git itself. Our Git repository is now the single source of truth for everything, and so that has to be secure. Git itself's been pretty secure over the years, and in most cases folks are using hosted Git services like GitHub, like GitLab for this, which have been also pretty good at security. But there are definitely some process-related things to consider. By its nature, Git can open you up to certain things, and we need to make sure that our users are aware of where those potential problem points are. So we will need to be doing things like enforcing two-factor authentication, making sure our users have strong key security practices, and that they're keeping Git updated locally. And exposing private data is always a risk here, particularly in commit histories or when we're working with repositories, moving them around. configuration data really shouldn't be in Git unencrypted, even in local repositories, for exactly that reason. So we need to help our users to be able to use things like git ignore for stuff like that. And it goes without saying that we need strong review processes. It's really all about the human aspect, making sure that our processes are correct and that folks understand what they need to do. And where we can, we want to be automating as much as possible, reducing that friction for being able to do these things. And we can do that through things like pre-commit hooks. And once we're confident that Git is secure, we can start to leverage automation. You know, on every pull request, we want to be looking for the same issues that we were catching at the local development stage. But this time, these things are obviously going to be automated. And the key difference is here that because these checks are automated, we're also monitoring for things that might have changed since a particular piece of code was committed. Perhaps an upstream dependency has changed. New vulnerabilities are discovered all the time. And code that didn't show vulnerabilities when it was first committed might now have some problems. So these monitoring scans over time will allow us to pick things up right in the code repository where it's relatively low cost to fix it. And our container registries also kind of fall into this category. Nothing's fixed in stone, so an image that looked fine when it was built might now be vulnerable. If your registry's got built-in scanning, take advantage of that, or use tools that integrate with your registry. And we need to be scanning on an ongoing basis, even if we haven't changed our images. That base image that we used to base our image on might have new vulnerabilities, and lots of people aren't rebuilding images unless, you know, things actually change. Another key integration point is our CI/CD systems. And again, we can automate scanning directly into our build pipelines. And we're looking for things that may not have changed, but because we're rebuilding things, we can catch any changes that might be happening upstream, things that have changed since that code was first scanned when it entered the source code repository. And then the final place we want to be looking is our production environments. Containers in production, particularly if they don't change very often, can end up with vulnerable images. So we need to be looking both at running containers and as a double check at new containers being spawned. In this space, we can also take advantage of admission control, perhaps things like Open Policy Agent, to ensure that our security policies are being reflected in the code that's being deployed. Perhaps we want to double check that our images have been scanned before they hit production, and we can actually stop things here from deploying into our clusters if they don't comply with those policies. And in the production space, we can also look at emerging practices around runtime, perhaps looking at anomalous behavior. And there's lots of emerging tools in that space which are going to be checking for unusual patterns that might be happening inside your cluster, which might indicate that a particular container has been compromised. So let's take a look at some of these areas in practice using Snyk. So let's start by looking at the tooling that's directly available for developers in their workflows. So the CLI is a good place to start, and here I have a checkout of a node application that's a clone from an upstream GitHub repository. And we can see here that we have a package.json file which is defining the third-party dependencies that this project is using. And so if I want to immediately test this from the CLI for vulnerabilities within those packages, I can just run snyk test from my CLI. That's going to detect this package.json, build a dependency tree of not just those dependencies that I've specified, but the dependencies that they have brought in themselves. And we can see that we have a wide range of vulnerabilities that Snyk has discovered in this particular package. And whilst it's great to see this information, this is not probably the most interesting part of this that I can now run Sneak Wizard from this repository, and Sneak will be able to make suggestions about how I can actually fix those. So actionable things by changing particular packages. We can see here that it's suggesting to upgrade the ADM zip package to 0.5.2. And if I accept that upgrade, it's going to make those changes in that package.json and actually fix that issue for me. From the CLI, we can also scan our container images. So I can see I've got a bunch of Docker images here, and if I want to test one of these for vulnerabilities, I can just do sneak container test Matt Jarvis Matt-node. And now Sneak is going to analyze that container image, look at the base image, look at all the packages that are included in that base image, and detect vulnerabilities in that container image. This is going to take a little while to run because it's going to build the dependency tree for the entire container. And we can see it's now querying the Sneak database. And again, we've been returned a whole set of issues that our scanner has found within that container image. So we've got integration into CLIs there, but we can also look at integration into our IDE tools. So this is VS Code running the Sneak vulncost plugin, and again we're looking at that package.json file. And we can see that Sneak, the vulncost plugin, has identified the same issues, but presented them within the IDE. So we can see for a particular package like this humanized package, we can see there's one vulnerability in that. We can actually view the problem directly from here. And we can also look at fixing those issues from within our IDE. So if I click on Quick Fix here, Sneak is going to suggest to us an upgrade pathway which will fix those issues within that particular package. So now if we go to look at the Sneak UI, this is my organization within Sneak, and we can see that I have a range of projects that I have imported from various sources. Some of these are imported from my source code management system. Some of them are imported from Docker Hub, and for each of these repositories, Sneak is not only going to scan this once, but because I've imported it into my Sneak organization, it's going to be scanning it on a regular basis. And so if we look at this node repository, which is the same repository we just looked at on disk, we can see that Sneak has scanned a whole range of things within this repository. We have our package.json file. And we can actually look in the UI at the whole dependency tree that Sneak has worked its way through. So like I said, it's not just looked at the dependencies that I've specified, but it's also looked at all the other dependencies that those have brought in, our indirect dependencies. So we can drill down on particular vulnerabilities and look at what that issue actually is. In this case, it's a directory traversal vulnerability, and we can see that Sneak is proposing an upgrade pathway which is going to fix that particular vulnerability. What we can also do here is to remediate things. As we said earlier, the most important thing is that we have actionable insights, because as developers we actually want to fix these things, and Sneak can actually raise PRs directly against your source code database. So if we were to click fix this vulnerability for this ADM zip package, it's going to raise a PR directly in this in the source code repository. We can click open fix PR. And we can see that it's created this fix PR directly in our source code repository. And it's going to have just put that simple change from our ADM package from 0.4.7 to 0.4.11. And with Snyk, we can raise these PRs automatically, or as we've just seen, we can raise them manually. So if we go back to our Snyk UI, we can look at some of the other things that that we've scanned within that particular import. And we can see we've also discovered some Kubernetes YAML files within this repo. And if we look at these, we can see that Snyk has also scanned these for particular security vulnerabilities. So if we drill down into one of these, we can see that this container's running as root. And Snyk will also tell us the impact of this and how we can resolve that, which setting we need in order to resolve that particular security issue. And then we've also discovered a Docker file in this repository. And using the Docker file, we can effectively rebuild the container image as it would be once we actually built it. And we can see we've discovered a very large amount of vulnerabilities in the base image that this container is going to use. And not only have we discovered those vulnerabilities and given information about how to fix them, but we've also been able to recommend a series of alternative upgrades, alternative base images, which are going to have less vulnerabilities in them. So by going from this current Node 6 stretch, which is pretty old, we could go to the Node current slim and reduce our vulnerability count to somewhere around 61. So if we go back and look at our package.json again, you might note these scoring here, these prioritization scores. And prioritization is extremely important because it gives us insights into which things we should fix first. And within Snyk, we not only use the CVSS score, which is the standard for scoring vulnerabilities, but also enrich that by things like how mature the exploit is. But most importantly, does a fix exist for this? Because if we have something that's a high vulnerability, a severe vulnerability that has an exploit in the wild that's mature and has a fix, then that's really a no-brainer for us to fix, because we can just upgrade the package and therefore fix that vulnerability. So enriching that scoring to enable developers to actually see which things are important, but also to give actionable insights into how we might move forward and fix things. And you can see here we have a whole range of filtering so that we can look at, perhaps we're only interested in things where there is a fix available, so that we can filter out things which are at this point unfixable. So if we now look at some of these other imports I have here, so this is the actual Docker image which I built from that repository and that exists in Docker Hub. So I've imported this project from Docker Hub. And we'll see if we look at this particular base image, that again, we've discovered all those same vulnerabilities within the Docker image itself. And from the Docker image, we are not able to make the suggestion about which base image we ought to upgrade to. So we can see here that we can link the Docker file from a different Git repository to this particular container image. And then we can get actionable insights again. And so if I look at, I think this one has the Docker file linked to it. I think it's this one actually. And we can see that, again, here we've got those same base image recommendations because we were able to look at the actual Docker file and detect which base image was actually being used. So that, again, actionable insights into how we can fix things. So Snyk will integrate with a very wide range of different elements within your software development lifecycle, a whole range of source code management systems, a whole range of container registries, including all of the major container registries that are out there. The ones that I've been looking at are coming directly from Docker Hub. We also have integration again with production, with things like Kubernetes, and with a whole range of CI/CD systems, as well as a wide range of IDE plugins. So you can see how you can plug this security scanning on an ongoing basis all the way through your software development lifecycle. So the takeaways from all of this is that we need to shift our security left. We need to empower our developers to make decisions about security based on modern tools and modern process. In this kind of new world, security teams aren't gatekeepers anymore with control over deployment. We need to consider the role of security professionals to be advisors and toolsmiths as opposed to gatekeepers, empowering our development teams to deliver feature velocity, new features and new code to production, and therefore delivering business value. And visibility and remediation of security issues needs to be baked in to each stage of our development pipeline. So we're leveraging automated tooling to scan third-party code, our container images, and our infrastructure code. So thank you for listening. If you're interested in trying out any of these features in Snyk, you can sign up for free at snyk.io/signup.